Hello mathematicians, we're now just going to have a look at factoring sums and differences of powers. Now this is a little bit of an oddity in this chapter. It doesn't really belong in this chapter. It's an extension concept and it really belongs with something called the binomial theorem, which we'll do later on. But I figure your brain's been fairly relaxed so far with this topic, so maybe we just need to give it a little bit of a stretch and a pound, and this might be the topic to do it. So, we start off talking about this pattern. Now, it calls it a polynomial. You don't know much about polynomials yet, but it doesn't matter. So if we looked at this pattern here, we can see that we've got a GP with the first term being 1, and the common ratio is x. So we multiply by x to get each successive term. From the formula for the sum of a GP, which we know is a outside of r to the n minus 1 over r minus 1, then our sum of a GP is a, which was 1, outside of x to the n minus 1 over x minus 1. Now if we take our x minus 1 on the bottom here and multiply it across, then we could write that expression like this. So we get that x to the n minus 1 equals this pattern here. Now, without any good reason, essentially, I'm going to say that more generally, when we factorize the difference of nth powers, we can write this. So basically, wherever we had a 1 here, I'm putting a y to the n, and if you look at this pattern here, and that's all it is, a pattern. We've got x minus y, x to the n minus 1 multiplied by y to the 0, which is 1, x to the n minus 2 multiplied by y to the 1. So as we go on, as the power of x drops by 1, the power of y goes up by 1, until at the very end we've got x to the 0 and y to the n minus 1. Now, that is a general expression for the factorization of the difference of nth powers. And we can check this out for what two formulas we know at the moment, the difference of squares and the difference of cubes. So if we put 2 in here, x squared minus y squared, we'll get x minus y times, when we put our numbers in here, when n is 2, we'll have x to the 2 minus 1, so that's x. All of these other things will disappear or cancel each other out, and we'll have y. So we get x minus y times x plus y, which we know to be true. If we did it with a 3 in here, we will get that x cubed minus y cubed equals x minus y times, and our first term here is going to be x to the 3 minus 2, so that's x squared, and on the other end we'll have y squared, and in between the only term which will turn up is an xy. So we know that one as well. But what this lets us do, ultimately, it's sort of just an oddity at the moment, is that it will let us get the difference of any cubes. Now, this, as I said, is a link between series and the binomial theorem, but it's a very vague link at the moment. Now, while we can't do a sum of squares factorization, at least over the real field, we can do it over the complex field, the sum of cubes we know that we can work out. So, we could use our knowledge of the sum of cubes and say that x cubed plus y cubed is actually x cubed minus y cubed. And if we go through and substitute minus y wherever we had y in our expression for the difference of cubes, we get this, and therefore we get that. So I suppose what we've done in a sense is that we've just shown where the sum and difference of cubes equations come from. And we can work out then for the sum of any odd positive powers, so it has to be odd and they have to be positive powers, then we could get this pattern here, which you can see is the one that we got a little while ago. When we had a minus there, all of these were pluses. When it's a plus there, every second one alternates and is a minus. Now, like I said, this is just a little bit of brain stretching at the moment, so I don't want you to do many of these. Maybe not even all of those from I to P, but have a little play. Have a go at 4A. This stuff won't turn up in your topic test. It's just there as a, to store away in the back of your mind, ready for binomial theorem later on.